In this video, we're going to construct another three-dimensional object by revolving a region around an axis. This time, though, we're going to revolve around the y-axis. We're going to use as a boundary our function y equals e to the negative x. So our negative exponential decay curve. We're going to start at y equals 0.1 and end at y equals 1. And that is going to leave us with a region indicated here. When we spin that region around this axis, we're going to get the shape that you see to the right there. This is obviously a complicated object. We don't have any formulas in our kit that will find the volume of that out of the box, so we need to take an approach like we had before of slicing this up somehow. Let's consider our options for that. What is the shape of any cut made perpendicular to the x-axis? So that would be any cut this direction. If we expand that out and look at it in 3D, that would be a cut in this direction, and that would look something like a little hump there, maybe something a little steeper, or if you go to the middle point, it would be this sort of peak shape. The upshot of which is this shape would be complicated and not something that we have formulas for, which implies not an easy way to get to volume. So in that scenario, we should probably try something else first. And one of the things that we can try is cutting perpendicular to the y-axis. So here's the y-axis. If we cut horizontally, perpendicular to that, then imagine what we get when we spin around that shape, and that actually is a nice circle. We'd have this region here, we'd spin it around, and with a circular shape, we can much more easily get two volumes. And we notice that every slice will be the same shape. The only difference that changes is the radius of the slices. We can certainly work through that. Once we have those circles, we'll be able to find areas or related volumes from that. That'll be our next step. We imagine then, looking on this 2D picture, taking a cut at height y and a thickness delta y, very much in keeping with our earlier approaches. When we do that, we're going to get a disk. That disk is going to have a radius, and it's going to have that thickness, delta y, and so the volume of that slice is going to equal the circle area times the thickness. We just break those down one by one. Circle area is pi r squared. The thickness we know already is going to be a small element of y, delta y. And our challenge next is determine the radius. Well, we can see the radius on this picture. That radius is in fact equal to the x-coordinate on y equals e to the negative x. This curve is defined by that negative exponential. And so looking for the radius this way, this is literally the distance from the x-axis to an x-coordinate, which is exactly what the x-coordinate means. And that can be found, if we know what y is, by rearranging this equation. This is the same as ln of y equals negative x, taking the ln of both sides, or negative ln of y equals x. And that gives us our radius. We take that and put it in our volume for the slice equation. Negative ln of y all squared times delta y. If anyone tells us what y is, what slice we're looking at, and the thickness of the slice that we want, we can then compute the volume of this structure here, and that'll be the one element of our sum to get the entire volume. That leads us to our last step, which is writing down the integral. The total volume is going to equal an integral adding up these slices, negative ln of y all squared. The delta y is the only thing that changes. We write it as a dy. We add the ingredients telling us where to start and stop. We were told that we are going to begin at y equals 0.1. So that's our lower limit. Our first slice occurs there. Then we slice, 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 and we stop slicing at y equals 1 exactly. So having found the volume of a slice, the integral lets us do the accumulation of the volume of all of those slices on the interval here of y values that we're interested in. We're going to copy this formula to the next page and then start evaluating the integral. But this is the challenging conceptual part. The next part will be the pure technical execution of an integration. At the beginning of any integral like this, it makes sense to tidy up first. Here we have a common factor, the pi out that we can bring out front, and the negative ln all squared, the negative goes away, and we can call this ln of y all squared. Now this is not something we can look at and know the antiderivative of. It also doesn't look very susceptible to substitution, which is our first go-to technique, because there's no 1 over y cancellation happening here. There's no inside-outside derivative relationship. So that leaves us to try by parts. And if we're going to try by parts, we really don't have many choices at all. The u part we differentiate, well, that pretty much has to be our ln of y squared, because whatever we put in dv we have to integrate, and we don't know how to integrate this. So that leaves just dy here as the element for dv. Our process for integration by parts is to take the derivative. Y is our variable. We'll try to be explicit about that. The other side here, we integrate both of these, and that eventually gives us a du being 2 ln of y times the derivative of the inside is 1 over y, and then a dy at the end. That would be over here in the derivative, and we just move it up. The other term is simpler. The integral of dv is v, and the integral of dy is y. Put our little mnemonic in here, and away we go for the calculations. This integral can be replaced by pi times ln of y squared times y, u times v, minus the integral over the same interval, 0.1 to 1, of y times this. And here we'll expand it out. The 1 over y and the y will cancel. In fact, we just get 2 ln of y dy. Only missing ingredient here is this has already been integrated or dealt with. We have to remind ourselves we will sub in the limits of integration into that as well. We do a quick round of tidying, and we get y ln of y all squared. We can bring the 2 out front. 0.1 to 1 of ln of y dy. And this, again, has those limits of integration that we'll sub in later. All right, we now have a new integral. This one is also a challenging one. Requires by parts integration. We've seen this one before, though, so we'll do the integration by parts here, but we won't go into gory details on it. We'll define our u value as ln of y, our dv is dy. That leaves us with du as 1 over y, and integrating this gives us y again. Little arrows for mnemonics. That will let us rewrite our integral as pi times y ln of y all squared. I'll hold off on this because we'll have more ingredients in a second. Minus 2 times the ln of y times y, or y ln of y, minus the integral of y times 1 over y. Oh, and I forgot the dy here. Let's make sure we include that. So y times 1 over y just cancels, and we end up with dy by itself at the end here. 0.1 to 1 put all of these in to be explicit. And then this last term here is just going to equal y when we integrate it. So it's a little horrible looking, but we'll copy it over to the next page and wrap this up. Here we have all that work copied over. The final integral step, going back a page, we had the integral of dy by itself, and out front of that we had a -2 and another negative, which gave us a +2 multiplier. We're now ready to apply the fundamental theorem by subbing in the value for y at 1 and y at 0.1, and getting a numerical value for the volume of this shape. Specifically, it gives us 1 times ln of 1 squared minus 2 times 1 times ln of 1 plus 2 times 1 minus pi times the same thing with the 0.1 in, 0.1 ln of 0.1 all squared minus 2 times 0.1 ln of 0.1 plus 2 times 0.1. All of this together is our antiderivative with the value 1 subbed in, and our antiderivative with the value 0.1 subbed in. Some of these tidy up quite nicely. The ln of 1s in particular are just 0 values. Ln of 1 is 0. That's about all the basic tidying that we can do. But we can rewrite this with the signs cleared up. We'll have 2 minus 0.1 ln of 0.1 squareds, and we'll have a plus 0.2 ln of 0.1, and a negative, and a positive makes a negative 0.2. And if we sub all that into our calculator, we end up with 2.5432. Like that. And if we put all that into our calculator, we get a value of 2.542 cubic units. The value itself is not of tremendous interest. What is of more interest is just going through that process and understanding how we can take this complicated geometric shape, build it out of smaller disks or thin cylinders, and get formulas for the volumes of those, and then use an integral and the calculations for antiderivatives to eventually end up with that volume calculation in the end.